So in the previous video, we have calculated the bending moments for the force system shown in this figure here. And I have mentioned at that point that because it's a lengthy topic, I'm going to split this into two videos. So we are going to assess the maximum bending moment and location of the maximum bending moment, and also draw the bending moment diagram for the system in this video. So if you remember, we have calculated the bending moments from equation 1, equation 2 here, and another equation 3 here in the previous video. If you have any confusion, have a look at the previous video here, and come back to this one. Now, we have assessed this force system by dividing it into three sections. This was the first section, this was the second one, and this is the third one. The bending moments for this we have calculated before. As I said, the first one is RB times X, the bending moment. That is RB times X, where X is the distance between the section and the load here, RB. So always we take the moment based on this point here. So you can see the matching color here. So moment is taken from that point. And in the for the second section, we have calculated the bending equation as RB times X plus 1 minus 5X squared. So that is RB times X plus 1 minus 5X squared, where X is the distance here, and this is 1. So the distance to RB from the point is 1 plus X, that is the distance used here, and in this case we have calculated 10 kilonewton acting at X distance, so the total load is 10X, and that can be considered as acting as a point load at the mid span of this length, that is X by 2. So that will be 10X times X by 2, that will give you 5X squared. We have discussed this in the previous video. And for the third system, we have calculated RB times 5 plus X minus 40 times 2 plus X. So that is RB times 5 plus X minus 40 times 2 plus X, where this is the distance X, and this is 4 and this is 1. So the distance to RB is 4 plus 1 plus X, that is 5 plus X, and the distance to 40 is the total load of this force system acting as a point load at the midspan. So that will be half of the 4, that will be 2 plus X, and the load is 40, so you have 40 times 2 plus X. So this is the equations. Now you can see this is a linear relation, as it is in the format of y is equal to f of x, and this is a linear relation. Therefore any line drawn based on this equation will be a straight line, whereas in this case this equation is the format of y is the function of x squared. Therefore this is a curve, because it's not a linear relation. This equation will give you a curve. And in the third one, this is again as in the case of the first case, it is y is equal to f of x, and therefore you will have a linear relation in this case as well. So we need to calculate the bending moments, the maximum and minimum bending moments, for which we allocate the values for x, and we did that in the previous video. Here x ranges from 0 to 1. Here x ranges from 0 to 4, and in the third case again x ranges from 0 to 1. So if you give a 0 and the first and second values of the x in these equations, you will get the maximum and minimum values. Now, to draw the bending moment diagram, I'm just going to extend this lines here. Let's draw these two lines here, and there is one more we need. Okay, and I'm going to draw a datum line as well to draw the bending moment diagram. And you have the points of intersection of or changing loads, which is, you have one change here and you have another change here, which is at the distances of 1 and 5. Now from the first equation you can calculate for the value of x ranging from 0 to 1. You have you have moments ranging from, at 0 moment is 0, and at 1 RB is 20, therefore 1 you have moment 20. So this is the first moment and this is the second one, and this forms a linear relation. So you have a 0 here and 20 here. So, and that is a straight line. So you will have 0 here and 20 here, and as I said, this is a straight line. Now in the last case you have again calculating x equal giving the values to x at 0 and 1. You have RB for the first value of x equal to 0. You have your moment values will be, at x equal to 0 moment will be RB times 5, which is 100, minus 40 times 2, that is 80. So 100 minus 80, that is 20. And for x equal to 1, that will be RB times 6, 40 times 3, so that will be 0. 120 minus 120. So first value will be 20 and the last one is 0. So again you have 20 here and 0 here. So I'm going to draw that as well, which is 20. Okay. So this is the first and last portions. We know that is straight. It's a straight line, not a straight line. It's a line at an angle, and the mid portion we need to calculate what the shape of that equation will be, because we know that follows y equal to f of x squared, or it follows a curve format, and we need to calculate the maximum and minimum bending moment for that. So at the extremes where x equal to 0 and 4, you will have the same as 20 and 20. I've discussed that in the previous video as well. So you have x equal to 0 and 20, the moments will be, at x equal to 0, that will be RB times 1, that is 20, minus x equal to 0, that is 20. So this term will be 0. And at x equal to 4, that will be RB times 5, that is 100, minus 80, that is 20 again. So at these two values you have 20 and 20, but you don't know the maximum value of that equation. In order to find the maximum, what you do is equate the first differential of that moment equation to 0. So d over dx of that moment equation equal to 0 will give you the maximum or minimum condition. So you have d over dx of that equation. So d over dx of this gives you the, so what is the d by dx of this equation? That will be, you have rb d over dx of rb x plus rb minus 5x squared. That gives you d by dx of rbx is rb, and d by dx of rb is 0, minus d by dx of 5x squared is 10x, and you equate this to 0, or you have rb is equal to 10x, or x is equal to rb over 10, that is equal to 20 over 10, that is equal to 2 meter. So at x equal to 2 meter, you will have the maximum value of that equation. Now to calculate the maximum value, you substitute this value in this equation. So you give 2, value of 2 for the x in this equation, and you get the maximum bending moment. So bending moment maximum is equal to rb times 2 plus 1 minus 5 times 2 square. So that is rb times 2 plus 1 minus 5 times 2 square. So that is 20 times 3 minus 5 times 4, that is 60 minus 20, that is equal to 40. So 40 is your maximum bending moment, 40 kilonewton meter. That is your maximum bending moment, and we know at the two extremes the values are 20 and 20, and the equation follows a square law, therefore it's a curve. That much we know. Now, so this is 20. Here you have 20 at these 2 points, and you have another value of 40 here, and in between these two it's a curve. So I don't know how effectively I can draw a curve here. So what I'm going to do is I'm gonna draw a straight line and see if I can bend that to a curve. Better than I expected. Okay, so yeah, so you have a maximum value of 40, and that will be here. What you need to make sure is that between these points and these points it is a straight line. So when you draw the diagram, give the feeling that this is a straight line, and this is a different equation and different curve. So you have the maximum bending moment here, and the the maximum bending moment is at 2 meters, so it's at the right at the middle of the line here. And because that's a symmetry case, it will be like that. There wouldn't be any surprises. And from this you can also draw the shear force diagram of this force system. That again is pretty simple. Once you have the bending moment, it's easy to draw the shear force diagram. So if you have the bending moment diagram, you can just use that to generate your shear force diagram. The RB and RA are 20. So at this point, you have a 20 kilonewton RB acting upward. So that is 20. And there is no other force up to this point. There is no forces in between this point and this point. So you have 20 going all the way to here. And from there, you have a uniformly distributed load starting at this the beginning point of the UDL, which is here, and the total load is 40. So 40 kilonewton will be acted through this 4-meter distance. So it starts here, and at this point it will be 40, total 40 kilonewton. So you can see that starts there and goes all the way down, crosses at the midpoint, and all the way down. The total force is 40. So at the halfway mark, it will cross the datum line, and then once it reaches this point, there is no other forces between here and here. Therefore, that load will continue up to here, and then you have your reaction at A, that is 20. So reaction at A will act upward to 20. So this will be your shear force diagram, and you can see that the point at which the maximum shear force, zero shear force, and the point of maximum bending moment are the same. That will be the case all the time. When there is a the maximum bending moment, the shear force will be minimum at that point. So you have 20 here, 20 kilonewton, and this is minus 20. This from 20 to minus 20, the magnitude of this will be 40 altogether. That is 40 kilonewton, which is the total load of this uniformly distributed load. 10 kilonewton per meter acting over 4 meter. The total load is 40, and therefore that brings this 20 down to minus 20 through this 40 kilonewton. And at this point, you have RA acting upward, which is 20, and therefore minus 20 cancels to 0 here. So that is the shear force and bending moment diagram for the force system. So we have calculated, in the first video, we have calculated the bending moment for the UDL, and we have located the point of maximum bending moment. We calculated the maximum bending moment, and we draw the bending moment diagram and the shear force diagram in this video. Once again, thank you for watching.